Good afternoon, everyone, and welcome back in the today 2-week faculty development program on MATLAB for engineers and scientists, bridging theory and applications. This is the fourth day of the faculty development program, and today the lecture will be on numerical methods and algorithms. And invited speaker in this session will be Dr. Amanjot Kaur from the Department of Physics and Baba Farid College, Batinda, India. So before inviting her, I would like to have a brief introduction. Dr. Amanjot Kaur is specialized in atom-light interaction, electromagnetically introduced transparency, nonlinear optics, and atom localization. Her research work is focused on the study of electromagnetically induced phenomena in multi-level atom scheme of rubidium. In addition, she studied influence of the closely spaced hyperfine level and wavelength mismatching effect on the EIT response of complex atomic configuration. Moreover, she used EIT scheme to obtain large-scale nonlinearity and enhanced atom localization in two-dimensional and three-dimensional sub-wavelength domain. She has published more than 12 research papers in international repute essay journals and also presented her work in the national and international conferences. She has also in-depth knowledge of performing data analysis using various softwares such as MATLAB, Mathematica, Origin, LaTeX, Canvas, Mendeley, and C++. Dr. Amanjot received DST Inspire Fellowship for carrying out her PhD research work. Dr. Amanjot, welcome in this session. And I hope that her expertise will be very helpful, informative, knowledgeable to all the participants who are joining this session, and some of the participants who are attending this session through the live streaming. If you have any question, you can put in the chat box. And all the audience or the participants who are attending through this Zoom meeting, I also request you, if you have any question, you can unmute your mic. You will be permitted now. Anyone can unmute your mic. But the thing is that you have to keep in mind, only required, you must unmute your mic. Otherwise, your mic must be muted. Okay. So now, first I have to assign Dr. Amanjot co-host. Yes, ma'am, welcome. And now you are co-host, you can unmute your mic. As well, you can share your screen. Over to you.
Good afternoon, sir. Am I audible?
Yes, ma'am, you are perfect audible.
Thank you so much for such a nice introduction. And thank you for making me a part of this 2-week faculty program. I really feel honored. So I'll start sharing my screen. So is my screen visible to everyone?
Yes, ma'am.
Thank you so much for informing. This is day 4 of the 2-week faculty program. And today we are going to discuss about numerical methods and algorithms in MATLAB. So this is the brief outline of my talk. So I'll start by discussing how to solve the system of linear equations using MATLAB. And there are 2 different commands to solve the system of linear equations. Then we will discuss how to solve the system of nonlinear equations using the F0 and Fsolve commands in MATLAB. Thereafter, we will discuss how to compute eigenvalues as well as eigenvectors in MATLAB. Afterwards, we will discuss how to perform numerical integration using trapezoidal as well as Simpson rules. And thereafter, lastly, we will discuss the numerical differentiation part using the MATLAB. So we'll start with first how to solve the system of linear equations using MATLAB. As shown on your screens, we have a system of, in general, we have this kind of system of linear equations. So what we normally do is we collect the coefficients on the left and right hand side, and we actually get two different kind of matrices. The first one is a square matrix, which is capital A. Then we have a vector containing the right side of these equations, which is B. And now how to solve this mathematically using MATLAB. The first command is lensolve a comma b, where a is the matrix, square matrix, and b is the matrix containing the vector components that were present on the right hand side. So this, I have actually shared the screenshot of the MATLAB code over here. So how to solve this set of this equation? For example, we have these three equations, that is x plus 2y plus 4z is equal to 1. Then we have this second equation, 3x plus 2y plus 4z is equal to 2. And similarly, we have this third equation. So we will start by defining SYMS XYZ, which means we have to define these three variables XYZ. These are symbolic variables. So whenever you have to write some symbolic variables in MATLAB, you use this command SYMS. Next, you will define all the three equations in MATLAB. So this is the first equation that I have defined. I've written in the comment section also, so that there will be more clarity. So I've added the comments after each code line. Next, I have written the second equation and similarly the third equation. Next, what we have to do is we have to convert these equations to matrix, and the command is equations to matrix. And in the bracket, we have the three equations as well as the three variables. And when we will run this command, we will actually get these two matrices A and B. Lastly, we will use the lensolve command. The syntax is lensolve bracket A comma B, and this is the solution that you're going to get. Now, these are the three vectors, that is x, which is half, then there is the value of y, 9/4, and lastly we get the value of z, -1. So now I will actually run this code in MATLAB and show you. So this is the code that I've just discussed. We have a set of equations x, y, z, and we have also used the command clc clear all, so that the variables are cleared whenever we run the program. So this is the code that I've actually shown you in the PPT slide also. So when we'll run this command, we'll run this file, but what we're actually going to get is this. Look at the command window. See, we have, let me just make the command window a little bigger. So we have these values, it is half, 9/4, and -1. So we get the solution. Also, we have another command for this. And the second command is solve. We can also use solve to solve a set of linear equations. So this code is similar up to this point. So we have defined the three variables x, y, z. Then we have defined the equations, and the command is solve. Solve equation 1, then all the other two equations followed by the variables name, that is x, y, and z. So this command actually solves this set of equations. And lastly, we have used the command dis. This means to display, and solution.x means you have to display the x part, that is the first vector of the solution. Similarly, this solution.y displays the second variable, and similarly the third one is solution.z. So this is what we are going to get. So I will now run this program in MATLAB. So here is this program. This is solve linear equations. So similarly to the previous case, we have used CLC clear and close all. Then we have written the set of equations, and then we have used these commands. And finally, when we run this program, what we're going to get is, see, if you look at the command window, I will make it a little bigger. So this is, we have half, 9/4, and -1. So both the commands, that is lensolve as well as solve, can be used to perform to solve the system of linear equations. The only difference is if you have a matrix, if you have a matrix, then lensolve command is much better because you already have a set of matrix and you can easily use directly the command lensolve a comma b. But if you have a set of linear equations, like for example in this case you had equations, so instead of converting them to matrix form, you can use the command solve and you can solve your set of linear equations. So both commands are good, but depends upon what is given in the question. If you have a matrix, then you can use lensolve. If you have a set of expressions, then you can use solve command. So this is all about the linear equations. Since this is a hands-on training session, so I will leave this problem as an exercise for all of you. So you can use these two codes to please solve these set of equations using both lensolve as well as some solve commands. And I've also displayed the solution over here. Next is how to solve the set of nonlinear equations. So if you have a single nonlinear equation, then you can use the F0 command in MATLAB. See over here, we have F0 command, which is used to solve a single variable or a single nonlinear equation of the form fx is equal to 0. The syntax for this command is F0, F name is the function name. For example, in this case, you have this function that is f of x. So here we will write f, comma x0. x0 is the initial point that you are given. So using this syntax, you can actually solve a nonlinear equation. For example, here is a question. You have to calculate the pi by finding the zero of sine function near 3. So since sine function is a nonlinear function, so what you will first do is first you will define this function. So I've used function fun at the rate sign. So we have already learned on the day 1 of this FDP that how to define functions in MATLAB. So I will not go into that. Next, we have specified the initial condition, that is x0 is equal to 3. And lastly, what is the command? It is f0, the function name followed by the initial point. And what you will get solution is 3.1416, which is actually understood because you know that the sine function is 0 at sine pi. So this value 3.1416 is actually pi. Okay, so we can actually run this code in MATLAB. Here is the code CLC, and then you will define the sine function and you will get the give the initial guess. This will be followed by this F0 command, and when you will run this, you're going to get is, see, in the command window, you're getting x is equal to 3.1416. Similarly, we can have another example in order to understand it more in a more better way. So here you have to find the zero of the function xq minus 2x minus 5. So if you have to, first you have to define this function. So what we are going to do is function y is equal to fx, and you have written down the function over here q minus 2x minus 5. Remember, you have to save the function in a separate file and then you will call the function in another script file. This becomes easy because you have a lot of functions in MATLAB, and if you define all the functions in the same script file, it becomes messy. So it's better if you define functions in a separate file and then you call it in the main script file. But remember, when you will save this file, it would be with the name f. Why f? Because whatever you write over here, the file name should be the same. Like for example, I've used fx, so this file will be saved with name f.m. So after saving this file, you will not run this file. This is a function file. And next, in another file, another script file, you will call this function. So in another file, I've called this function at the rate f. Then I have also mentioned the initial condition, that is x0 is equal to 2, which was given in the question because you have to find the zero of fx near 2. And lastly, you will apply the command, which is f0 function comma x0. And this is the solution that you're going to get. So I'll run this code in MATLAB. So here it is. So first we have defined the function, and see over here, we have defined it with the name f.m. And then you save this file And lastly, you will go to another file and then you will call this function first, and then you will provide the initial point. And lastly, you will run this program. You're eventually going to get, see, z is equal to 2.0946, which was the answer. So this is a simple command that you can use to solve a single nonlinear equation. But what about if you have multiple nonlinear equations? In this case, the F0 doesn't work. Then you have to use the command fsolve. The syntax is primarily similar to that of F0 command, but the F0 command only solves a single nonlinear equation, while fsolve actually solves a set of nonlinear equations. So what you will do is, this is the same syntax, fsolve followed by the function name and then the initial guess. For example, we have a set of nonlinear equations over here. These are two equations which are nonlinear. We have to solve it using the MATLAB. So what will you do? Yeah. So firstly, you will take these two equations and define them in a separate function file, as we have done in the F0 case. So you have taken a function file with the name NLE. And remember, whenever you will save this file, the name should be nle.m. Then we have written these two equations. Remember the last two equations which shown in the previous slide? x1 minus 4x1 square minus x1 x2. That I've written over here. This is the first equation and this is the second equation. And then we'll end this function file and we will save this. Next, in another script file, you will provide the initial guess, that was 1 and 1, and then you will apply the fsolve command. So fsolve at the rate nle because the previous function file was saved with this name, comma, the initial set of points. And lastly, this solution you're going to get, which says that fsolve has been completed, and this is the resulting solution, which is 0.25 and 0. So let me run this code in MATLAB. See, so this is the first file, NLE, and we have defined these two functions over here. This would be followed by this. First, we will save this file. I've already saved it. Next, in another script file, you have written the initial conditions, and then you will apply the fsolve command. When we will run this program, we are going to get is x solution, which is equal to 0.25 and 0. So this is the method to solve the set of nonlinear equations in MATLAB. Before continuing further, I would leave this problem as an exercise for you all to solve. So you can easily solve these nonlinear equations in MATLAB using the fsolve command, and this will be the resulting solution. Our next goal is to compute eigenvalues as well as eigenvectors using the MATLAB. So we know that if we have a square matrix of an order n, then how you calculate roots in mathematics, you apply the command a minus lambda I is equal to 0, and when you do this, you get the eigenvalues of the matrix A. And corresponding to these eigenvalues lambda, we have a set of eigenvectors. And how do you compute eigenvectors? The formula is Ax is equal to lambda x, which is a minus lambda I multiplied by x is equal to 0. Obviously, we know that if the eigenvalues are distinct, then we get linearly independent eigenvectors. Otherwise, it's not possible to always get linearly independent vectors. So our target is to find lambda and x, but not manually by using MATLAB. So this is the normal traditional way that how you calculate the equation as well as eigenvectors corresponding to any matrix. For example, here we have a matrix with four coefficients, 1, 2, minus 5, and 4. And this is manually, this technique is quite difficult to solve because it's quite lengthy. But in MATLAB, you can easily solve for eigenvalues as well as eigenvectors in just 1 or 2 minutes. So what you have to do is you have to define this matrix first. You have already, I think it has already been discussed in the day 1 itself, how to define a matrix in MATLAB. So we'll define this matrix and then use a simple command to compute the eigenvalues as well as eigenvectors. So let me show you. We'll go again to MATLAB. So this is the code. Yeah. See, just a 5 lines code that you can use to calculate the eigenvalues as well as eigenvectors. So this is the first command, eiga. And this is the second command. eiga means you will get the eigenvalues corresponding to this matrix. By the way, we have defined this matrix. This is the first row followed by a semicolon and then the second row. So when you will run this command, you will get the eigenvalues of A. And next we have a second command which contains two matrices. First matrix I have defined with the name vectors. Vectors means this particular vectors will actually consist of the eigenvectors corresponding to the two eigenvalues. And then we have a diag matrix, which means a diagonal matrix whose diagonal entries will actually specify the eigenvalues of this matrix. So let me run this. It would be more clear. See, I will make the command window a little big. Yeah. See, the answer is -1 and 6. So this particular answer we have got against the command eiga. So we are getting two eigenvalues, -1 and 6. And these are the two vectors. See, this is the first vector, -0.7071, -0.707. This is the eigenvector corresponding to the value -1. And this is the second one, which is corresponding to the eigenvalue 6. Also, we have a diagonal matrix. See, we have a diagonal matrix with two non-zero entries, which are nothing but the eigenvalues of this matrix. So just by using a simple command, which is this one, essentially this one, we can compute both the eigenvalues as well as eigenvectors of a matrix in just 1 minute. So this I'm leaving as a problem for you all. So you have to compute the eigenvalues as well as eigenvectors of this matrix in MATLAB. And this is the solution that is written over here. We have a set of vectors corresponding to the three eigenvalues that you will get. And this is the diagonal matrix. So next we are going to discuss is numerical integration using MATLAB. So we know that analytically many techniques are available for numerical integration, but why do you need MATLAB for numerical integration? So there are two cases basically. The first one is there are cases when the function is not known, but some data is given in the tabular form. So in this case, the function is not given. So how will you integrate? And the second one is the function is given, but the function is very difficult to integrate. For example, this function, you can't directly integrate using your manual techniques, this exponential x square function. So these are standard integrals which have values you can directly write down there, but you can directly integrate. So in the last slide, this is what I was talking about. So if you have some data in tabular form, for example, this is the data, which is velocity versus time. So this is time and this is velocity. And you have to integrate this tabular data to compute the distance. Now, this is quite tough. If you will use the manual techniques, you can do this. And similarly, we have this function ex square. If you want to compute its exact numerical integral, it is not possible. So you have to resort to numerical techniques. So how do you do that? Numerical integration in MATLAB is performed by using Newton-Cotes formulas. What are these Newton-Cotes formulas? In this, you actually replace the actual integral by approximate integral, approximate function. So what kind of function? For example, here we have a curve f of x, is shown by this. This is a black curve, is the actual fx curve. So you're going to approximate this curve by a straight line between the initial and final points. And when you do this, we're actually using the trapezoidal rule for the numerical integration. Similarly, if we have this curve and we approximate it by using a second or third order polynomial, for example, this dashed blue curve is actually a polynomial which is used to approximate this f of x, then we are actually using the Simpson rule. Simpson's 1/3 as well as Simpson 3/8 rule for the numerical integration. We will discuss these one by one and we'll see which one of these is better for computing the numerical integration. So the first one is trapezoidal rule. So what we do in trapezoidal rule is, I have already told in the previous slide also, we replace the actual function by a straight line. So the integration is actually the area under this curve. So how will you calculate the area under this curve? This is a trapezium. So we have the endpoints, the final points minus initial points, and then you have to compute the function at these 2 points divided by 2. So this is the trapezoidal rule. Okay. So the problem with the single trapezoidal rule is that it doesn't yield accurate results. So what we normally do is we actually split this whole curve into a number of trapeziums. For example, there are 2 trapeziums. Similarly, we can have multiple trapeziums. The advantage of separating the whole curve into multiple trapezium is that we get a more accurate answers. So in this case, the formula becomes this: h naught by 2 f x naught. X naught is the initial point, f xn, which is the last point, and all the another points. This is the formula for that, and that is I from 1 to n minus 1, fxi. So we'll use this formula in MATLAB actually to calculate the numerical integration using the trapezoidal rule. So first, let me discuss the trapezoidal rule only. So here we have a numerical. We have a function which is x squared by 1 plus x cube. We have to integrate it from the limit 0 to 3 with n is equal to 10. This is the number of trapeziums using the trapezoidal as well as Simpson rules. So firstly, we will find h. H is the interval or the step size, which is 3 minus 0, b minus a divided by n, that I've already told you. This is the formula. So we will perform the numerical integration. Remember, the formula for the trapezoidal rule is this. Go to the previous slides. Just remember this formula. The first point, the function calculated at the first point, the function calculated at the last point, and all the another points are within this summation, multiplied by a factor of 2. So let me go to the code. So this is the MATLAB code. So the first command is f is equal to input, enter the function. So you will have to enter the function. This command says this. Next is second command, enter the number of trapeziums. Next, you have to enter the lower limit and then the upper limit. Then I have defined h. H is equal to final point minus the initial point divided by the total number of trapeziums. Next, you will define a sum function. Why do you need a sum function? Because remember, in the formula of this trapezoidal rule, we have this term which is summation from I is equal to 1 to n minus 1. So we'll initiate a sum function with initial value 0. And next, we will use a for loop from I is equal to 1 to n minus 1. And the sum function will actually sum all the function values ranging from I is equal to 1 to n minus 1. So this is the command sum is equal to sum plus the value of function at a plus h. Then you will calculate at a plus 2h, similarly up to n minus 1. Then you will sum all the values. So lastly, we will apply the formula, which is h by 2. Now remember the formula, the first value function at the first point, then at the last point, and in the center there was a term 2 into sum. So I have written over there. Lastly, you will print your result. Your result is actually stored in the variable tr, because we have defined this variable tr. So we'll write the result using trapezoidal. This is a string. Whatever you will write within these 2 commas will be printed as such. The main part is percentage 0.6f. What do you mean by this 0.6? Means whatever result you will get will have 6 decimal places. After a decimal, you will get 6 significant figures, and f means a floating number. Remember what is a floating number? So any number in which you have after you have digits after your decimal, that is a floating number. So you have to print in that. So let me see what the result is. The result is shown over here after the arrow. See, enter the function. So first we will enter the function. And always you have to use this @ command, because remember on the first itself you learned how to write the functions. And then you will enter the function. In our case, the function is x square by 1 plus x cube. Then you will enter the number of trapeziums, the lower limit, upper limit, and this is the result using trapezoidal rule. I have also printed the true value. True value I have actually calculated from the Google itself. You can find the exact value of this interval. This is the true value. And you can see that our result is accurate up to 3 significant figures. After that, the result deviates. So let me run this code in MATLAB for more clarity. So here we have this numerical integration. This is the code that I was talking about. I have just shared a screenshot of this with you. Now let me run this. See, first on command window, we have enter the function. So I will enter the function over here. See, then it will ask me enter the number of trapeziums. So these are 10. Next, you have to enter the lower limit. Figures, the result is accurate. You can actually make the result more accurate by increasing the number of trapeziums. For example, if you take, I will again run this code. So here we have the same function. Now we are increasing the number of trapeziums for better accuracy. Let me take them 100. Then the lower limit is same. The upper limit is again 3. So this is the result. Now see, the result using trapezoidal rule is 1.1107. Up to 4 significant figures, the result is accurate in comparison to the previous case. So you can actually get more accuracy by increasing the number of trapeziums. So this was all about the trapezoidal rule. Next, let me move to the Simpson rule. So we have two Simpson rules. First one is Simpson 1/3 rule, in which we approximate this curve, the original f of x, which is shown by the black line, by a polynomial, second order polynomial. So the resultant expression for I is b minus a by 3 and f x of 0, which is the initial limit, f x of n, which is the last limit. And in between these two, we have two sums. The first sum runs over the odd indices, that is 1, 3, 5 up to n minus 1. And the second sum runs from over the even indices, 2, 4, 6 up till n minus 2 into the function. So you have to remember this formula in order to implement the Simpson rule in MATLAB. So remember this, we have one sum over the odd indices and we have another sum over the even indices. So let's start writing the MATLAB code for Simpson rule, 1/3 rule. We will again consider the same integral, that is x squared by 1 plus x cubed. So this is the code. The initial lines are similar to the trapezoidal rule. We have to input the function, we have to enter the number of trapeziums, then we have to define h, the sum, and all that stuff. This is the main line. We will start from odd sum is equal to 0. We have initialized a variable. Remember, you have to sum over 1, 3, 5 up to n minus 1. So your for loop starts from j is equal to 1 in steps of 2. So after 1, what would be the next point? 1 plus 2, that is 3. And after 3, what would be the next point? 5. 1 plus 2, 3, then 5 up till n minus 1. So this is the odd sum. First, you will find the odd sum. Similarly, you will initialize a even sum with value 0. And the even sum will run from 2. Then next point would be 2 plus 2, 4. Then 6 up till n minus 2. So even sum is equal to even sum plus f function. So this will compute the summation of all the even terms. Lastly, we'll apply the formula, which is h by 3 into f of a plus 4 times odd sum because remember the formula, the odd indices would be multiplied by the 4 and the even indices would be multiplied by 2 plus f of b, and you will then print this result. See, I've also shown the command window result on the right hand side. You have to enter the function, trapeziums, lower limit, upper limit, and this would be the results using Simpson 1/3 rule. So let me go back to the code, although I have previously run it. Let me run it again. We'll take so enter the function. Let me make this command window a little big. @x. So we are entering the number of trapeziums 10, lower limit 0, upper limit 3. See, the result using Simpson, I think there is some problem. Yeah, I've entered the wrong function. So let me again run it. Yeah. So now if you look at over here, the result using trapezoidal rule was 1.1100. The fourth significant was 0, but in the true answer, the significant figure was, the result was 7. But using Simpson rule, what you're actually getting is 1.1105. Clearly, the Simpson 1/3 rule is much more accurate compared to the trapezoidal rule. So it approximates the function very well. Similarly, we have one more rule, which is the Simpson 3/8 rule. Let me discuss that also. So in this case also, we approximate the function using a polynomial, but in this case, the polynomial is not a second order polynomial, but a cubic polynomial. So when you do that, the result is this 3b minus a divided by a10. Now you have two summations. The first summation is 4 into f of x1, x2. These are the functions which are not the multiples of 3. And then you have another summation that runs over all the function values that are multiples of 3. Okay, so you have these two summations. Remember this, we have a group of functions which are not multiples of 3 multiplied by a factor of 4. Then we have these functions which are multiple of 3. Then you have to multiply it by the factor of 3. And lastly, FA and FB are as usual. Earlier also we have written those. So now we will write the code for these. So this is a Simpson 3/8 rule. What you're going to do is you will define sum 3 is equal to 0. This is the sum that runs over all
Dear participant, there is a small technical issue from speaker side. Please keep patient and stay connected. Thank you.
Sorry, I just encountered some network issue. Am I audible?
Yes, ma'am, you are audible.
Okay, thank you so much, sir. So what I was telling was, share my screen as well. Sir, would you please allow me to share my screen?
Well, kota
Yeah,
Ma'am,
thank you.
please share your screen.
Okay, thank you so much, sir.
Yes, yes.
Yeah. So as telling was how to implement Simpson 3 8 rule. So first we will sum over all the multiples of 3, then we will sum over all the indices, because we don't know how to extract only the multiples of 3. In earlier case in Simpson 1/3 we have either the odd indices or the even indices. In this case we have either the multiples of 3 or the numbers that are not multiples of 3. So what you will do is you will calculate the total sum, which is defined by this function, that is sum, and then you will subtract the sum that was corresponding to the multiples of 3. So this is the total sum, and this is the sum corresponding to all the function values that were the multiples of 3. So eventually what you will get is sum not 3. Sum not 3 means the sum of all the functions that are not the multiples of 3. Lastly, you will implement this rule by using this command, which is 3h by 8 into f of a into 3 sum not of 3 plus 2 into sum 3 plus f of b. So this is the result of command window that I'm sharing on the right hand side. You have to enter the functions, enter the number of trapeziums, the lower limit as well as the upper limit, and lastly we will get the result using the Simpson 3 8 rule. So I've already implemented this code in MATLAB several times, so I will not run it again. So this is the result. Clearly, if you will compare all the 3 rules, the best result we get is using the Simpson 1/3 rule. Of course, if you will increase the number of trapeziums, all the rules, that is trapezoidal as well as Simpson rules, will give the accurate answer, quite accurate answer. But as far as the best one is concerned, the Simpson 1/3 rule gives the best answer. So you have to prefer that. Okay. Yeah. So next, I have already discussed in one of the previous slide that if you have given a tabular data, it's impossible to integrate it analytically. So the only option you have is the computational techniques. So if you have a tabular data, I've already shown some tabular data in one of the previous slides. So this is the tabular data we had. That is, we have the value of time ranging from 1 to 5. Then we have the value of velocity from 10 meters per second up to 20 meters per second. So how to integrate this data? I am using the numerical integration. The thing is easy to do because you can either use the trapezoidal rule or the Simpson's rule to actually integrate this data. So this is the code that I'm showing you. See, we have this sample tabular data in which we have entered the time values. Then we have entered the values of velocities. Then we have defined a function length t. Length t means how many total number of elements do you have in the time as well as velocity array. Clearly, when you will, if you don't use the semicolon, you will get answer 5 because we have 5 number of entries in time and we have 5 entries in the velocity as well as. So we'll start integral 0, which is similar to that previous case that we have used, that is sum is equal to 0. Then we'll perform the numerical integration. So I have used a trapezoidal rule over here. You can use Simpson rules also. So I from I is equal to n minus 1, the integral plus again the similar formula. You will calculate it, the function at first value, then a value which is 1 additional to the previous value divided by 2. You know the trapezoidal rule is simple. And lastly, you will print the integral using the, it's very easy. You just have to apply the for loop and use any one of the three rules, that is trapezoidal or Simpson rules. And this is the final integral value that you're getting, which is 4.5. So let me run this code in MATLAB. So this is the data I was talking about. So I will not go into details of the code. I've already explained it. So let me run this. And in the command window, what we are getting is the value of this integral is 4.5. Lastly, I will leave this problem as an exercise for you. You have to calculate the integral value of this function exponential x square by using the numerical integration in MATLAB. So you can use a similar code that I have already shared with you. You just have to, in the first line of the code, when they will ask you to, when MATLAB will ask you to input the function name, instead of x square by 1 plus x cube, you can enter this function and you will easily get these three results using the three rules. So next, what we are going to discuss is the numerical differentiation using MATLAB. So again, why do you use numerical differentiation? If we can actually we have techniques to derive numerical derivative, sorry, we have techniques to differentiate the functions analytically also. So there are two cases. In first cases, when you don't know what is the function and you have some tabular data, as in case of the integral numerical integration also. And the second case is again similar to the numerical integration case, that is you have a function which is very difficult to differentiate. For example, if you will actually have to differentiate this function as x power x power x, it is very difficult to differentiate this function. So you have to resort to numerical differentiation techniques. You have no other option. So these are the two cases in which we have to use the numerical differentiation. So how do you use it? We have some numerical formulas to compute the first derivative. The first formula is forward difference formula, in which the derivative at any point x is given by the function value at one step further minus the function value at the present divided by h. Similarly, you have a backward difference formula in which you actually calculate the function at x and then you calculate the function at one step backward, that is x minus h divided by h. Then also we have a central difference formula. We can use either three of them to calculate the derivative. Depends upon at which point you have to calculate the derivative. If you have to calculate the derivative, for example, you have a range of values from x1 to 10. If you have to calculate the derivative at x is equal to 1 or 2, you can use the forward difference formula because x is equal to 1 or 2 lies at the starting only. Okay, if you have to calculate the derivative at some point, for example, x is equal to 9, then you have to use the backward difference formula. Otherwise, central difference formula is the most accurate one, which we'll see shortly. Then we have 3-point formulas also, which are more accurate compared to the 2-point formulas, in which we have a forward difference formula. 3-point means you have to actually calculate the value of the function at 3 different points, and then you can use those formulas to calculate the derivative. You have to just remember these formulas, and then you have to insert these formulas into MATLAB code for getting the answer. Next, we have some formulas also to compute the second derivative. These are the 3-point formulas. Again, 3-point because you are evaluating the function at 3 points. So this is the first one, second, and the third one. So these formulas are actually used to compute the second derivative of the function. Next, we have central difference formulas to compute. If you want to compute some higher order derivative, let's say third or fourth derivative, you can use this formula. So I have mentioned some of them up to the fourth order derivative. So let me take some example and show you how you can calculate this derivative using MATLAB. So we have function x square plus 5x. This is a very easy function, so I'm just taking it as a sample. Otherwise, you can actually differentiate very complex functions also. So you have to calculate the first as well as second derivative of this function using the 2-point as well as 3-point formulas. So we know that how do you calculate the analytical solution? It's fairly easy. Just differentiate this function. You can just, by looking at this, you can differentiate it. This is 2x plus 5. And suppose you have to find the function value at x is equal to 6. So you will put these values, you know that the analytical answer is 17. And similarly, if you find its derivative once again, we will get f double derivative of x, which is equal to 2. So remember these two values. We will see which of the 2-point formulas, namely forward difference or center formulas, will actually yield the correct answer. So this is the MATLAB code I'm sharing that is used to compute the first order derivative and second order derivative. So first, fairly long code, but it's very easy. So the first line is input, enter your function. So it says enter your function. So first you will enter your function, you will enter the step size, and next it will ask you which derivative you want to compute. Either you want to compute the first derivative or the second derivative. So in this case, since we only need two derivatives, so I have restricted my code to 2. Okay, otherwise I could have multiple derivatives. But you know, if you have the third derivative of this function, you are not going to get anything. It's 0. So we will not do that. So we have either the first derivative or the second derivative. So this is the formula. See, if d is equal to 1 means if you are actually going to calculate the first derivative, what will be your code? This is the first formula, fx plus h minus f of x divided by h. This is the forward 2-point formula. Similarly, you also have a backward 2-point formula, which I have shown by the term BD2, fx minus h divided by h. You can use one of the three, but I am using all of them to show which one of these is the most accurate one. So in addition to the 2-point formulas, we also have 3-point formulas. Remember, I have already shown you what's the expression 4 into fx plus h minus fx plus 2h minus 3f of x. If you don't remember this, you can just go back over here and you can just take these values and insert over there. So we either had 2-point formulas or 3-point formulas to calculate the derivative. Once you evaluate the derivative, next command is disp. I've already told you disp is used to display the results using the 2-point formulas, and then you will print the value. See, percentage 0.4 means you will actually get the values up to 4 decimal places, comma FD2. FD2 means you have to print the value which we have got in this variable FD2. Okay, then you have to also print the values corresponding to other formulas, because we have used backward difference also, central difference also. Even we have used the 3-point formulas also to compute the first derivative. Or this is if, okay, and the other part of this loop is else if. Else if means if your derivative is not 1, then your derivative could be 2, means you have to find the second order derivative. So what you will do is, see, then we have only three formulas, that is 3-point formulas. We have forward 3-point, backward, and a central. Remember, I have already shown you the formulas. These are the 3-point formulas for calculating the second derivative. Okay, then you will print the results corresponding to these 3 formulas. And the last command is else. Else means if you're not computing the first derivative also, not computing the second derivative also, I am going to display is that formula is not available. that I don't have any formula. Although I have, but I actually don't have to calculate either I only want the first derivative or the second derivative. Okay, if you want the third derivative of this function, you can actually use this formula also. I have already told you this is a formula which can be used for the third order derivative. Since I don't require over here, so I have not used it. Okay, so let me run this code now. So this is the result you're getting on the command window. First, you will input the function. You will enter the step size, which derivative you want to compute. For example, I want to compute the first derivative. At which point do you want the approximate derivative? Is the x is equal to 6. Remember? And if you remember the analytical solution, here it was at x is equal to 6, the derivative was 17, the first derivative, remember? And the second derivative was 2. So let us check which formula gives the correct answer. If you see the Newton forward formula, it gives the answer 18, which is not accurate. And the backward difference formula gives the answer 16, which is also not accurate. The central difference formula actually gives the best result, which is 17. Similarly, the 3-point formulas are much more accurate compared to the 2-point formulas. You will get the answer 17 in both cases. So since I have actually entered which derivative you want to compute is first. So these are the results I'm getting. The results will obviously change if you change here, if you replace 1 by 2. So let me just run this code in MATLAB. It will be more clear. So we have this numerical differentiation. See, this is the code. So let me run this. See, it's asking we have to enter the function. So what was our function? It was, remember, you have also have to use @x. It was x here plus 5 into x. Okay, let me make this command window a little bit clear. Enter the step size. So I can take it 1. You can even take it much lower depending upon how accurate you want. Which derivative you want to compute. For example, I want to compute the first derivative. At what point do you want to approximate derivative? That was x is equal to 6. These are the results that have already displayed. So let me now run this formula for the case in which you have to calculate the second derivative. Let me run this code again. So step size is 1. Now I want to compute the second derivative. Remember, what is the analytical solution I'm getting? The answer should be 2. And I have to calculate the derivative at 0.6. So the result using 3-point formula is 2. So you are getting the exact result using the codes, MATLAB codes. So I have covered the numerical differentiation as well. So that's all from my side. If you have some questions, you can please ask me. Is anyone having any questions?
Hello.
Hello.
Hello, ma'am. Is it audible, ma'am?
Yes, sir.
Ma'am, my name is Nataraj, ma'am. Actually, I have a couple of questions, ma'am. The one is, suppose if my function is hyperbolic or else logarithmic, then is there any specific kind of code for it? Like,
No, you can use a similar code. What you want to do actually, you want to numerically differentiate it or you want to integrate it.
no, in terms of integration.
Yeah, you can use the similar codes. You just have to enter the command. Like for hyperbolic, there is some specific command, like you have to enter the function. For example, if you have to enter the cost, you use COS, then you, for hyperbolic cost, you use some another term. Just have to remember the MATLAB commands. Otherwise, the formulas are same.
Okay.
Mhm.
So this means, like, for example, sin hx e power x plus e power minus x by 2. So for
Yes.
this, directly the formula it is there.
Yes. If you even write exponential of x and exponential of minus x divided by 2, even if you integrate that also, you will get the results similar to that of a sine function, because these are one and the same things. Just you can't write e over there. You have to write exp. That you have to just specify, because MATLAB doesn't recognize the symbol e. So you have to write
Yeah.
exp. Yes.
Okay. And the second one is, what is the maximum like step size that we can take it?
Maximum means what is the step size that we can actually take?
Yeah. So as you mentioned, it has up to 1, you said. So
Yeah,
more.
we can go down to actually 0.001 also, but it will take some time, long time to run the code. But there is a limit. The limit is defined by the memory that a MATLAB can allocate for a particular program. So if you exceed that memory, you are not going to get the result. But 0.001 up till that too, we can get the result. So it's quite good accuracy that we can obtain. But the price you pay is that it takes longer to run that program, much longer compared to when you take h is equal to 1.
Okay.
Yes.
Thank you. Thank you.
Thanks so much. Any other question? Is there any other query from any participant?
Hello?
Yes, sir.
Yes. Thank you for the presentation. It's quite good and very clear. Yeah, and it also gives a lot of insight, particularly with the aspects you just brought up about the numerical differentiation
Mhm.
of the 3 points and all the others. I just want to know, I don't know what your plans for the lecture is. Normally, when we compute numerical solutions, we also try to consider the error.
Yeah, error.
In this case, yeah, you are not particularly about the error, although you mentioned that some methods are more accurate and better than some others. But I know there are tolerance limits that we need, and we need to see the error margin, particularly whenever we compute and we tabulate. We always have a section for the error. So I don't know. I mean, are you still going to discuss something that relates to the error for all these numerical methods that we are discussing? Thank you.
Okay, thank you so much, sir. For error, I have not actually shown that in my code, but you can easily write, for example, I'll just show in the command window. You can just write error. You will have to define a function named error, and then you will write absolute. Absolute means the absolute, only the magnitude, not in terms of sign. Okay, then you will write the true value that you are getting minus the value that you have got using the code. For example, in trapezoidal, you have actually used the variable tr to represent the value that you've got. If you actually enter this command within the function file, and if you run that, you will actually get the error also associated with the code. So you can use this command. It is absolute true value minus the value that you have got using some code. That will give you the answer.
So the error formula is already embedded in MATLAB. Is that what it means?
There is a formula. There is a formula. Even for trapezoidal rule also, there is an inbuilt function, trap z. I have actually not used that because I wanted that you know how to write the loops, because otherwise we don't have that idea how to actually write the code from scratch. So I didn't use those inbuilt functions over there. So we can easily use trapz command also for getting the answer by using the trapezoidal rule. But using a lengthy code which you write from scratch enables you to actually learn the MATLAB codes in a much easier way. Once you get accustomed to that, you can easily use the trapz functions also. There are inbuilt functions. Even for Simpson rule, we have a function. There's quad function to integrate. But then we don't know how to write the codes like from the scratch. So that's why I've shown you how to use the looping to get the results.
Thank you for that. Thank you.
You're welcome. Any other question?
Hello, ma'am. Am I audible?
Yes, sir.
Ma'am, when we are using 0.6f
Yes.
floating numbers, so
Mhm.
is it truncating the next digits, or it is giving us the round of result?
It is actually giving the round of results.
Okay.
You can actually check that by going to 0.7 or 0.8 also. So
Okay.
it is actually rounding off the result, not truncating them.
Okay, ma'am.
You can use that. You can use up to 0.8, even 0.12. People use up to 0.12 also for 12 significant figures. But 0.6 is fairly accurate. You can use up to that.
Okay, ma'am. Thank you.
Yes, welcome. And any another question from the participant side?
Hello.
Yes, sir.
When one question is related to,
Mhm.
I have any equation in the tensor mathematical calculations. So, is there any technique to solve tensor mathematical calculations in MATLAB code?
To define
If
tensors,
we,
because
yes,
tensors are actually matrices only. Yeah, like we have a tensor of order 2 or order 3 there, but there are MATLAB commands for that also. For example, if you want to multiply, have a Kronecker delta product, because normally when you multiply the tensors, it is not the normal multiplication. You can define the tensors using matrices. Like basically you have a tensor product. That is the main thing, because tensors are eventually the matrices. So you can define matrices like normally we define matrices in MATLAB. And then when you have to do the product of those tensors, okay, you can use specified functions. For example, Kronecker delta is a function that is used to multiply two tensors. You can't use normal multiplication over there. So it's a little deep. You have to understand those basics, like the addition or the multiplication in tensors is not the normal ones that we usually do, but there are some specific functions for that. So you can just look up into any MATLAB textbook and you will find those.
yes. Then one more question is,
Yes.
let us suppose we have a potential which is the combination of real and imaginary part.
Yes, sir.
How to deal with imaginary part in MATLAB?
Okay, so you can just define that function, and if you want to extract its imaginary part, you will write imag, imaginary. It's a command for that, and within the brackets, you will mention the function for which you want the imaginary part. For example, you will first define the potential v of x, and then if you have to calculate the real part, you will write real in the brackets v of x. Similarly, for imaginary, you will write imag in the brackets imaginary part. And if you will then want to plot it, you can plot it also.
Yes. Ma'am, if I want to separate real and imaginary part of the potential using the MATLAB, then can I do that?
Just the similar command I've told you already. You have to define that function first. Then in the second line, you will write the real of that potential and you will get the real part. That's the command REAL in small letters. In the bracket, you will get the function. Similarly, for the imaginary part, like for example, let me show in the command. See, for example, I have this complex function z is equal to 3 plus. If I want to extract the real part of this function, I will use this command. There is some error. I guess I have not cleared the variables. This is, and this, you get the imaginary part set. So see, when I write imaginary of z, I get the answer 3. Similarly, if you want to compute the real part, you can write REAL in the bracket z. So you can easily get that.
Okay. Ma'am, but actually in this function, it is clearly visible. 2 is the real part and 3 is the imaginary part. But if I have the potential, this is not clearly visible that what is the imaginary, what is the real part. And actually I am working with the cornell potential, modified form of cornell potential. And the real and imaginary part separated out with the help of Fourier transform calculations and all the lengthy processes by hand. Can I solve it with MATLAB code?
No, you have to then write those function because what I'm sort of getting from your question is that you want eventually you want to plot that function, its real as well as imaginary parts, or you want the values. You have to actually run a for loop also for that purpose because you have to find the value of that potential at many points. And at the last, you have to sum that function. If you want the plot of that potential at like the plot of imaginary portion of that potential, you can run a for loop and then you can plot it, but don't end that for loop. With all the points at every point, you will get like a plot, and then that plot would be like whole. You don't have to end that for loop before the plot ends.
Okay.
And the command is this only. Command is as simple as this because I've also used these techniques for quantum plotting in MATLAB.
Okay.
Yes.
And actually, my potential look like 2 sigma over md square minus alpha e to the power minus mdr plus 2 sigma over md square r alpha minus 2 sigma over md plus alpha
Okay.
md.
It doesn't matter how complex your potential is. You can do one thing also. You can use the function called complex expand. There is a function in MATLAB in which you can actually expand that complex function into real and imaginary parts using that command. So there are 2-3 more commands also. You have to check which one actually suits your potential. So if real and imaginary don't work, then you can use those commands also.
Can you share about those commands?
After this session, I can drop my email over here. I will share all the commands with you.
Okay. Thank you.
Welcome, sir. Any other question from the participant side?
Hello.
Hello.
Good day, ma'am. My question is that can we get the PDF notes on this workshop?
I didn't understand your question, sir. Can you please repeat?
He's asking whether we can have the hard copy of the presentation, apart from the video,
Okay. No, sir, the organizer will be sharing the PPT with you after this session. So they have already asked me to send the PPT as well as the script files. So they will be made available to you after this session.
Thank you for that.
You're most welcome, sir.
Hello, ma'am.
Yes, sir.
I said, please, how can we solve a Laplace inverse using MATLAB?
Laplace equation is a differential equations. So you have to use ODE solvers for that. There are commands like ODE45, which are the inbuilt commands. Then you have the differential equation solving methods. For example, there's the Euler method and then there's Runge-Kutta method, all the differential equations method. So you have to make a MATLAB code for these differential equations.
But I said, please, is there any video or little document that you can refer me?
Okay. Even Professor Machan sir has his own YouTube channel. So I've seen some heat equation, which is essentially sort of that Laplace equation only. So you can check out his videos. They are available on that channel, MTTF channel, with his name, Dr. Machan sir.
Dr.
Machan, who is the organizer of this.
Nechan, that is Nechan.
Yes.
Nechan.
Yes, you can check out his YouTube channel for the same. So he has actually 4-5 videos related to this differential equation solving, which is actually the heat equation. So which is
Yes.
essentially similar to that kind of stuff.
Yes. Thank you, ma'am.
You're most welcome, sir.
Hello,
Yes, ma'am.
can you hear me?
Yes, ma'am.
Ma'am, is it possible to solve any fractional differential equation with the help of inbuilt MATLAB commands?
There are inbuilt commands for differential equations, ma'am. I have already told you that there is ODE45 for for example.
Ma'am, that is for ordinary, it means like the derivative with integer order. I'm asking about fractional order, ma'am. Like 0.5, 0.1. Is there any inbuilt command? I'm working with fractional derivatives.
Okay.
All the time I used to go with the programming only. Is there any shortcut methods? That's what I'm asking.
Okay, shortcut methods. Right now,
Yes,
I'm not
ma'am.
remembering them, but just in case, like for example, I have discussed today the numerical differentiation. It is only valid if you have that step size, which is not varying, which has some regular step size. But if you want to compute it at some random points, like for example, friction points, you have to change the formula. You can't resort to these formulas, which are 2-point or 3-point formulas. We have divided difference Newton formula for that. If you have to compute,
It is in the case of different intervals, ma'am. I'm talking about if, for example, if the first order differential equation means dy by dx, we are mentioning.
you're talking about differential equations.
Yes, ma'am. A differential equation, if the power is ranging between 1 to 0 to 1, if the derivative is ranging from 0 to 1, in that case, I am asking, ma'am.
Okay.
Fractional derivative.
We have to look for the formula first, which formula you have to use, because right now I'm just not able to recapitulate which formula do you use for that. Once you get that formula, if we have some inbuilt command for that, because as far as differential equations are concerned, I only remember about the Euler's formula and then Runge-Kutta method. These are just easily available.
Yes, ma'am. These are very easy. Because I'm
Mhm.
working with fractional derivatives,
Yeah.
so all the time it is you need to write the code. That's what I'm
Good,
asking.
yeah.
Is there any built command for fractional derivative?
Okay, right now I'm just not able to recapitulate that, but maybe I can just message you later about the exact command, because I have to look at the
Okay.
formulas also, that which formula
Okay,
do they use.
okay, ma'am. Sure. Thank you.
You're most welcome. Any other question from the participant side?
No, ma'am. Thank you.
You're most welcome.
Dear participant, if you have any more question, please. Even you can unmute your mic to put your question. Thank you, ma'am, for your nice presentation.
Thank you so much, sir.
The content you present very nicely, and all the questions during the session has been discussed. I hope that the content will be very informative, knowledgeable to all the participants. The feedback form and the quiz will be shared in the WhatsApp group you will get after a few minutes. Thank you to all. Thank you. I want to check if there is any question in the chat box also. Okay, in the chat box, no question. Okay. Ma'am, thank you once again for this wonderful session. And dear participant, tomorrow we will join at the same time. And I request to all the participants, please join the session at least 10 minutes before the commencement. Okay. Thank you to all and have a nice day.
Thank you, Prof. Have a nice day too. Bye-bye.
Bye.